This is Unit 5, Nuclear Chemistry, Part 1 Notes. By the end of the unit, you should be able to describe the characteristics of alpha, beta, and gamma particles. You should also be able to describe the radioactive decay process by balancing nuclear equations, and you should also be able to compare fusion versus a fission reaction. When nuclei are unstable, they can undergo nuclear reactions to become more stable. And nuclear reactions differ from actual chemical reactions or normal chemical reactions due to the emission of nuclear particles. So the rays and the particles emitted from a radioactive source, that's called nuclear radiation. And then there are three types. There's three types of nuclear radiation. And you should be able to identify all three particles. The first ones are known as alpha particles. You may have remembered, or you can recall, an alpha particle from the gold foil experiment with Rutherford, because he shot alpha particles. They're similar to a helium atom, except that it only contains 2 protons and 2 neutrons. So this particle has an overall positive 2 charge. On the other hand, beta particles, these are an emitted electron, and if you know that electrons are negatively charged, you have that -1 on that bottom left-hand corner. Recalling isotopic notation, X is the symbol, Y is the mass, Z is the atomic number. So if you have an atomic number of -1, it is an electron. The atomic number of 2, that's the element helium, except that it differs because it only contains protons and neutrons. Gamma rays are electromagnetic waves that are usually emitted after alpha or beta emission. So these can occur through pretty much any nuclear type reaction, and it's really only just considered a form of energy with no mass and no charge. Hence, you have the gamma symbol and 0 and 0. So just to recall, alpha particles are a helium atom with a mass of 4 and a charge of 2. Beta particles, that's your emitted electron with a mass of 0 and a charge of -1. Then your gamma rays are just electromagnetic waves of a form of energy with no mass and no charge. So there's a couple of characteristics that you need to know about alpha, beta, and gamma particles. Whenever they figured out or identified the charges of the 3 radioactive particles, they used a radioactive source and they shot the electrons through a magnetic field of positive and negative charges. And the fact that alpha particle is a positive 2 charge, it was attracted towards the negative side and it was repelled by that positive magnet. The gamma, whenever it was shot straight through, the fact that it has 0 charge and 0 mass, it was not affected by either magnet, so it just had a straight projectile. And then your beta has a -1 charge, equivalent to an electron, so that's why it was attracted to the positive magnet and repelled by the negative side. So you need to be familiar with the charges of all 3 particles. So the charge of the beta, like an electron, the charge of gamma is 0, and the charge of your alpha is a positive 2. You also need to be familiar with the penetration ability of the 3 different particles and how they can be stopped. So if you're ever in an alpha, beta, or gamma fight with some radioactive guns or radioactive sources, all you would have to do is to stop an alpha particle. You would just hold up a piece of paper. Beta has it's the middle penetration ability because it needs to be stopped by a 0.5 centimeter lead block. And then gamma has the highest penetration ability because you have to use a 10 centimeter thick lead block to stop that radiation source. And if you recall, if you ever have any x-rays whatsoever, you have to wear one of those really heavy coats or like a really heavy piece of cloth. Those are your lead blockers, and it stops the radiation from going to the rest of your body, especially when you get x-rays of like broken bones or anything. So again, alpha has the lowest penetration ability, beta has the middle, and then gamma has the highest, and you need to know the 3 sources or the 3 things that can stop those radiation particles. The last one, it relates to tissue damage in comparison to its ionization ability. Alpha particles have a very high ionizing ability. That means whenever it hits the skin of the surface of your skin, it can be ionized very quickly, and that's why it does not penetrate past your skin or the surface of your skin. Beta has a middle ionizing ability, so it has to go deeper inside to your tissues before it becomes ionized and it stops moving. And then your gamma has a really low ionizing ability. That means it can go very deep into your tissue, hitting your organs before it becomes ionized and it stops going through again. So the higher the ionizing ability, or the higher the ionization ability, the less it can travel through your body, because that means it forms an ion and then it stops. So the alpha has the highest and it stops at your skin. Beta has the middle and it can go into your tissues. And then gamma has the lowest ionizing ability, so it can penetrate deep inside of your organs. Okay. There's other types of radioactive particles that exist because some nuclei can become very unstable. And then they are known as electron capture and positron emission. So electron capture occurs when there are too few neutrons relative to the proton number. So your neutron to proton ratio is too low. So to increase the stability, the nuclei converts a proton to a neutron. And this occurs by an electron that is captured by the nucleus, by its own electron is captured by the nucleus during that process, and it overall increases the stability because it increases the neutron to proton ratio. Recall the atom simulation that we did a couple weeks ago. Whenever you added in neutrons, multiple neutrons, it becomes unstable. So if you have an unstable neutron to proton ratio, it will emit, or it will capture an electron to make it more stable. And an example down here, whenever you capture an electron, it combines with the atom. So the electron of that carbon atom, the nuclei turns that proton into a neutron, and then hence your proton number decreases by 1. But your mass stays the same because the proton is converted to a neutron. They have equivalent mass numbers, so the mass never changes. But the only thing that does change is the element, because whenever it captures that element, it turns into a different one. And that's electron capture, where the electrons are being captured by the original element. Then you have your positron emission. That occurs also when a proton changes to a neutron, just like electron capture, except, hence the name, emission. So we have capturing down at the bottom left side here, and then we have emission at the bottom right-hand side. So again, this positron is equivalent to an electron, except for the fact that it has a +1 charge now. So your positron is like an electron, except it has a +1 charge, still a mass of 0, and that one is emitted through this positron emission process. So again, if you look at these equations down at the bottom left and bottom right, electron capturing is capturing that -1 charge, and then positron emission is emitting a +1 charge, but you can still form the same elements. So it all depends on which nuclear decay that you undergo. However, you need to identify that electron with a -1 charge as an equivalent beta particle. However, this positron has a +1 charge, and that is completely different from anything else that we've seen so far. So this is a data table summarizing all of the radioactive particles that we just talked about. You should be able to identify all the particles and their symbol, along with their charge and mass. And for just alpha, beta, and gamma, they're the only ones that you need to know their penetrating power and their ionizing ability in order from lowest to highest. So just to review, alpha particle is equivalent to a helium atom. It has a +2 charge and a mass of 4, hence the mass number and atomic number. It has the lowest penetration ability. It can be stopped by a piece of paper. And it has the highest ionizing ability, so the skin can stop it from protruding into your skin. Beta particle is equivalent to an electron with a mass of 0 and a charge of -1, and it is the middle guy. So it has the middle amount of penetration power and can be stopped by 0.5 centimeter lead, and it can go into your tissues because it has a middle ionizing ability. Gamma is the Y with a 0, 0, so charge of 0, mass of 0, has the highest penetration power, so you have to use a 10 centimeter lead block, and it has the lowest ionizing ability, so it can go all the way into your organs before it stops. Positron is like an electron, except it has a +1 charge, but still a mass of 0. And then your electron, that's equivalent to your beta particle, again, has a -1 charge and a mass of 0. And the only thing the electron is important for is the electron capture, or if you tell me that a beta and electron are the same thing, you'll still get credit. So again, this chart you need to write in your ISN so you can study the particles later and be able to identify all the particles based on their symbol, charge, mass, and again, just the first three for their penetration power and ionizing ability. So the next part of this unit is being able to balance nuclear equations. And if you recall, back in biology, you went over photosynthesis and cellular respiration, where your reactants yield your products. And we'll be using this yield symbol as a sign that a reaction is happening. So to balance nuclear equations, there's really only 2 rules to follow. And that shows you the decay process of those radioactive particles. But if you follow the 2 rules, you'll be able to get these questions correct every single time. Where the first rule is the sum of the mass numbers. Recall your X, Y, Z. So the sum of all the Y's, or your mass numbers on the reactant side, is going to be equal to the sum of the mass numbers on the product side. So really, the reactant side is equal to the products. And then the sum of the charges, that's the Z, of the reactants is going to be equal to the sum of the charges of the products as well. So really, you just want to have the left side equaling the right side in both the Y's and the Z's. And we can create algebraic equations from those chemical reactions to solve for the unknown. And I'm going to show you how to do that with these bottom 2 examples. Okay, so if we have this first example, it says to balance the nuclear equation representing alpha emission of uranium-238. So again, the uranium is the name, that's the mass number, using our isotopic symbols. So then uranium-238 is on top, and 92 is on the bottom. We know it's 92 because that is the atomic number. You can just look at a periodic table to get that number. Okay, and then undergoing alpha decay, alpha is the helium atom, and then this X, Y, Z, this is what we have to solve for. So setting up my algebraic equations, the first rule says that the sum of the mass numbers on the reactant side has to equal the mass numbers of the product side. So every time you see this yield, you're going to identify that yield arrow as an equal sign. So the top mass numbers, 238, is going to be equal to 4 plus my Y, because those are all the mass numbers on top. And then your bottom equation is going to be the sum of the charges on the reactants is going to be equal to the sum of the charges on your products. So you set the bottom numbers equal to each other. 2 plus Z. So solving for Y using algebra, Y is going to be equal to 234. And then solving for Z, Z is going to be equal to 90. So Y is my mass number. Z is my atomic number. And then how do we figure out this X symbol? We use the periodic table, look for the atomic number 90, and that represents the element TH. So that would be the answer to example number 1. Okay, so anytime you have a nuclear equation that we have to balance, you're either going to be identifying the element that it decays to, or you need to tell me the radioactive particle that it decays to. So in the second example, we're balancing the nuclear equation representing the decay of carbon-14 to nitrogen-14. So remember, those are the mass numbers. That's why 14 is on the top, the atomic number 6 on the bottom, and it's going to decay into nitrogen-14. 14 is the mass number, and now it has an atomic number of 7. Okay, so again, I set the masses equal to each other using my algebraic expression. And then you set the bottom numbers equal to each other. Recall that anytime you see the yield arrow, that is where your equal sign should be. So my Y, using algebra, is going to be equal to 0, because 0 plus 14 is still 14. But now my Z, what plus 7 yields 6? Okay, -1. So I have a mass of 0 and a charge of -1. That is represented by my beta particle. And that would be example number 2. Okay, so you're either telling me the element, like in type problem example 1, or you're going to report the radioactive particle that it decays to by setting the mass numbers equal to each other on both the reactants and the product side, and also the charges as well. Okay, so what I want you to do now is press the pause button, see if you can balance these nuclear equations, and then press play, check your answers, and then correct any mistakes that you did. Okay, so figuring out our missing x, y, z here, we set the masses equal to each other, 40 plus y. Then we set the charges, 19 equals 20 plus z. So my y is equal to 0, and then my z is equal to a negative 1. And then we need to figure out the symbol here, where my mass is 0, charge is negative 1. That's equivalent to a beta particle or an electron. Okay, number 2, we have our x, y, z, where y now is going to be equal to 0 plus 60. And then our z here is going to be equal to negative 1 plus 28. So y will be equal to 60, and z is going to be equal to 27. So how do we know the symbol for something that has the atomic number of 27? We look on the periodic table, and the atomic number 27 is going to be equal to your cobalt. So your answer here would be cobalt as the symbol, 60 as the mass number, and then 27 as the atomic number. And number 3, again, we have our x, y, z. We set our masses equal to each other. And then we set our charges, z is equal to 2 plus 82. So y is going to be equal to 212, z is equal to 84. So looking on the periodic table, what element has the atomic number of 84, which is, I think, PO, if I'm not mistaken. Taking a look real quick. 84 is PO. So you write PO as the symbol, 212 as the mass number, 84 is the atomic number, box in your answer, and that is a balanced nuclear equation. Then our last one, again, we have our x, y, z, where we set y is equal to 32 plus 0, z is equal to 15 plus negative 1. So your y is going to be equal to 32. Your z will be equal to 14. So then you look on the periodic table, what has an atomic number of 14? That is your silicon. So you write the symbol Si, mass of 32 at the top, atomic number of 14. Ooh, that's a 14. On the bottom, you box in your answer. And again, we follow the same 2 rules, where the sum of the masses on the reactant and the products are equal to each other. That's why every time you see an arrow, that is going to be your equal sign. And then we set the bottom charges equal to each other. Use algebra, and if you're not able to identify the radioactive particle, you're going to be looking on the periodic table to get that symbol X, if it's anything other than the 2, the plus 1, or the minus 1. Okay, and the last objective of this unit is to compare fusion versus fission reactions. And definition, fission breaks down large nuclei into smaller nuclei. So if you look at this example here, you have uranium. It's one large nuclei or nucleus, and it's going to break up into 2 or more smaller nuclei. So fission is breaking apart. On the other hand, fusion is creating large nuclei from small nuclei. So you see these 2 hydrogens coming together, and then they're going to form helium. So whenever you have 2 smaller nuclei fusing together to make something larger, that's fusion. So fission is breaking down, fusion is fusing together and making it larger. Fission reactions, those are like your nuclear reactors. We can't control those, and we capture that energy. So if you have a nuclear power plant, that's what's happening, is the fission process. So we have nuclear power plants. Fusion, the conditions required for this are too extreme to control. So you need to think about the sun. The sun is a big fusion process, and it releases a lot of energy, and we're not able to control that, obviously. Otherwise, we would have already learned how to capture energy from the sun. But it's too much for us to handle, I guess, in this day and age. So the sun cannot be controlled. That is a fusion process. However, both of them, they require large amounts of energy, and they're both considered nuclear processes, hence this is in nuclear chemistry. But the main thing that you need to get from this slide is understanding the difference between what fission is and fusion is. And we can also use examples on our radioactive decay balancing equations to identify whether something is splitting up or if two reactants are fusing together to make something larger, which we will practice in class. But just to reiterate, fission is breaking down large nuclei into something smaller, and then fusion is fusing two small nuclei, two or more, together to make one large nucleus. Okay, so have you accomplished the objectives of this unit? If you're able to correctly identify alpha, beta, and gamma particles and their characteristics, or if you're able to balance radioactive decay equations and compare fusion and fission reactions, then you have accomplished the objectives. If there's anything that you have questions about, please highlight, circle, star, and then the next time we talk about this through our lecture, please ask me all those questions. Thank you.